All right, everybody. In order to understand this video, you definitely need to understand context-free grammars. Try a few out, see if you can write a couple. And in this specific video, we're going to talk a little bit about derivations, precedence, and ambiguity, right? A couple of features of grammars and languages that we need to kind of cover. One is derivations are often written as a tree. The way this works is when S, in this particular grammar right here, when S is replaced by ASB, it is parsed out like this, where I'm showing you all of the things that S is replaced by in a tree. It is possible that you have multiple things being replaced at the same time, and we will see that in a second. The reason the parse tree is useful is it can show you precedence, but it also can kind of start to hint at how a machine might use a grammar to parse out a string, and that becomes important because grammars are used in all of your programming languages to kind of sort out what it is that your code is supposed to be doing. So let's take a look at a new grammar. Here it is. And I want you to show a parse tree for 1 plus 1 times 0. Okay, so go ahead and pause the video and show me a derivation and then a parse tree. You don't have to do both. Show me a parse tree for 1 plus 1 times 0. Okay, pause. Hopefully you're back now. And if you do this in kind of a full classroom, you'll usually get 2 different parse trees, and they look like this. So it turns out this same string is generated by 2 different parse trees. And these parse trees are important. One, because you see this kind of grouping on the right of e's, right? And then the other, you see this grouping on the left of e's. Now, if you think about what's going to happen first, this is going to force the plus to happen first, and this is going to force the star to happen first, the multiply, right? So you're going to get 2 different answers, right? On this side, this expression is going to evaluate to 0, whereas on this side, this expression is going to evaluate to 1. This becomes very important when you have operator precedence. Often, you can still get operator precedence out of a grammar by pushing the rules into separate variables. And so I'm going to show you an example of that. I will say, while we're at it, though, there's something important. This grammar is ambiguous because there is some string that the grammar can generate in 2 different ways. So we would call this grammar ambiguous because there is some string that the grammar can generate in 2 different ways. So grammars can be ambiguous. It turns out that this language is not ambiguous because we can write a different grammar that forces this precedence. And what we do is we put the multiplication deeper in the grammar so that it happens first. Really, the matching for plus happens first, but the multiplication happens first once you draw out the grammar. So here is a parse tree for that same expression, 1 plus 1 times 0. And you can see that because this multiplication is forced to happen down here in the t's, that there is no choice for us to kind of try to do the multiplication first and the matching. So the multiply actually obeys precedence. It happens first, and we get the right answer. So we would say that this language isn't ambiguous or inherently ambiguous, but the original grammar, this one, was ambiguous. But because there is some grammar that generates the strings in a non-ambiguous way, the grammar itself, the language itself, is not inherently ambiguous. So there's 2 terms. Ambiguous applies to grammar. Inherently ambiguous applies to languages. This language of addition and multiplication with binary numbers is not inherently ambiguous. This grammar is ambiguous. This grammar is not ambiguous. So here's our definition. Problematically, perhaps, there are some languages that are inherently ambiguous. There is no tree that you can ever make that does not, there is no grammar that you can ever make that does not have an ambiguous parse tree for this language. So we say that this language right here is inherently ambiguous. Now, what is this language? This language is A's followed by B's followed by C's, and either the number of A's matches the number of B's or the number of B's matches the C's. And it turns out that no matter which way you write the grammar, your parse trees for some string in the grammar, maybe not all strings, but some string in the grammar will have an ambiguous parse tree. So I've drawn the grammar that recognizes this language here. You can see it starts off with what if the A's and B's match followed by any number of C's that you want? That's one option. Or what if we have A's followed by the number of B's and C's are matching? So G is the B's match C's, A is the A's match B's, U1 is C star, and U2 is A star. So if you generate a parse tree for something like ABC for this, you should be able to find two different parses. And one of them is going to start with AU1, and the other one is going to start with U2G. And since nothing ever goes back to those states, there's no way that those parses are going to look the same in the end. And this is an example of an inherently ambiguous language. I point this out because while this is really fun to have ambiguity in English, I find that it makes it really fun. It's probably not great for your programming languages, but it happens all the time in natural speaking. For example, if you write this sentence, they are flying planes, right? And you try to break down what does this mean? Well, unfortunately, English is an inherently ambiguous language, and there's at least two different parses for this particular short sentence. And it could mean that you have a bunch of kids flying remote control planes, or a bunch of pilots actually flying planes. Or it could be, you can imagine a kid pointing up into the sky and saying, hey, those planes up there are flying planes. And so it all depends on whether flying is attached to which word, right? So ambiguity in grammars is not uncommon. We probably want to avoid it for our programming languages. And we need to be aware of it for our parsing and for our automation. And our automation has to kind of make some decisions related to that, perhaps sometimes, or will work in different ways based on which parsing mechanism you use. So it's important for us to think about in terms of programming languages, and that's why we bring it up. Okay, all right. Well, that is parse trees and ambiguity kind of in a nutshell. It would be useful for you to kind of come up with some languages and produce some grammars for it. So I would recommend that you do that at this point so that you can get more handy with what that looks like. But at this point, I will let you go. As always, be kind to each other. And in order to do that, you need to be kind to yourself. See you all next time.